Right, today we're going to talk about section 11.4 about implication and equivalence. Okay, so two statements are called logically equivalent when they have the same truth value for all combinations of the truth value of the simple statements involved. So logical equivalence means that they have the same truth value regardless of the truth value of the statements involved. So if the statement involves P and Q, then regardless of whether P and Q is true or false, the two statements have the same truth value. Meaning when you look at the truth table with these statements, that the column for the one is identical to the column for the other. That's what it means. So an example of a logical equivalence we just looked at, and we looked at this at the last lecture too, P implies Q is logically equivalent to not Q implies not P. Okay? The implication and the contrapositive are logically equivalent. But actually, there's another thing this is logically equivalent to. And we're going to show this in detail in a moment. It's logically equivalent to not P or Q. So there's actually an or statement that is actually the same thing as the implication statement. So that's a little bit odd. But that's kind of nice because that means you can actually define all this logic with just and, or, and not statements. And I'll make my not the book's not here. So let's draw a big truth table and make sure that these three statements are in fact logically equivalent. True, true, false, false, true, false, true, false. Okay. P implies Q we've looked at before. That is only false in the instance when P is false, when P is true but Q happens to be false. Not Q implies not P. Well, if Q is true, then the hypothesis fails and the implication is automatically true. So I can put true in those two. Now, if Q is false and P happens to be true, that's bad because we would have not Q, but we do not have not P. So we put a false there. And then lastly, if they're both false, that's totally fine. And now we can see the logical equivalence because these two columns are identical. Now, let's look at not P and Q. Not P or Q. First, we have Q in this first row, so that's fine. We do not have not P, and we also do not have Q, so the second row is false. But when we don't have P, this is automatically true. So as strange as it would seem, the statement of if P, then Q is logically equivalent to not P or Q. Okay, but they're logically equivalent because the truth table column is the same thing. Okay. Now there's a table on page 512 of the textbook that lists many equivalences. And we'll actually use that table again in another guise on Friday when we cover the next section. And so that's an important table that you'll probably want in front of you when you're doing the homework assignment, and you may want to have access to, say, on an exam or something like that. So you should be familiar with this table. So I'm going to write down a few of the logical equivalencies from the table, and we'll take a look at them. For A says P or Q and R is logically equivalent to P or Q and P or R. This looks a little bit like the distributive property of multiplication over addition. And it is, in fact, sometimes called the distributive law for logic. So let's make sure that this thing is true. Let's see what we get here. So I need a pretty big table for this one because I need P, Q, and R. So I'm going to have 8 outcomes. And then I need P or Q and R. And then I need P or Q and P or R. Okay, true, 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 false, 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 true, true, false, false, true, true, false, false, true, false, true, false, true, false, true, false. Okay, my table's ready to go now. So let's take a look at P or Q and R. As long as P is true, this statement is automatically true. So I'm going to put true for the first 4. I'm not even going to care about Q and R because it's an or statement and P happens to be true. Now, for the next 4, P is false. So I need both Q and R to be true. And that only happens here. The rest are false. Okay. Because P is always false, so that means this or needs Q and R to be true, and Q and R is only true in the first one of those last 4. So we get true, false, false, false. Are we good with this column? Okay. Are any of these fishy? Getting no feedback whatsoever. Okay, let's move on to the next one. Okay, now we need P or Q and P or R. Okay, these are 2 or statements. And whenever P is true, both of the or statements are true, right? Whenever P is true, both P or Q and P or R are true. So I can just slap some trues down here, because that's when P is true. Now, if P is false, I need both Q and R to be true to make this and statement true. Right? Because if P is false, the only way to have P or Q is to have Q. And if P is false, the only way to have P or R is to have R. So I need both Q and R because there's an and statement in the middle of those 2. And there we go. And we can see now that those 2 columns are identical. And so this is logically equivalent. There is a similar statement for B that I'm not going to detail, but it says that P and Q or R is logically equivalent to P and Q or P and R. This is another distributive law. So this is the way that and or interact with each other in more complicated statements. Okay, let's take a look at another one. 8a. Not P or Q is logically equivalent to, oh, and I should make my not the right way here. Not P and not Q. Okay. So a not statement outside of an or switches the or to an and puts a not in front of both of these. This one and the next one that we're going to do are called De Morgan's laws. De Morgan's laws are how you negate an and statement or negate an or statement. Now, have we heard that name before, De Morgan? We heard it in the set theory, right? In set theory, De Morgan's law was the complement of A union B is A complement intersect B complement. And the complement of A intersect B was A complement union B complement. And you can see why they might be both called De Morgan's laws. They change a symbol from being right side up to upside down, or vice versa. So maybe we picked these symbols correctly. Okay. Let's show that this statement is true. So this is a smaller truth table. We only need the 4 choices now. True, true, false, false, true, false, true, false. Okay, the third column, not P or Q, is going to be the opposite of P or Q. Okay, P or Q, I'm going to erase this, but we're just call P or Q would be true, 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 false. That's P or Q, and so I want the opposite of that. And now we'll just get rid of that. So that's not P or Q. Then not P and not Q, it needs both P and Q to be false. So that only happens here, and the rest of the time it fails. And we see that those 2 columns are the same, and so this is a logical equivalence. And then the other De Morgan's law says not P and Q is logically equivalent to not P or not Q. And maybe I won't detail that one in the interest of getting through enough stuff and leaving a little time for you to get started on problems here. But it's a similar situation. Okay. Now let's look at 12. Now, there's something called, there's a logical operator called little c, which means a contradiction. And we'll see how this works in a moment. But this says P implies Q is logically equivalent to P and not Q implies C. This is a little bit weird, but I'll show you how this works in a moment. So now we have C is a contradiction. And as everyone knows, a contradiction is always false. So here's the table. True, true, false, false. True, false, true, false. False, 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 false. Something that's always false. Okay. Now, let's look here. Let's now add P and not Q. Okay, so there's P and not Q. The only way for P and not Q to be true is for P to be true and not Q to be true. So that's why there's only one T there. Okay. So, now, let's look at this final statement, P and not Q implies C. Okay, if P and not Q is false, then this is always true, right? If the hypothesis is false, and the hypothesis in this implication is right here, if the hypothesis is false, the implication is vacuously true. It's always true. And now, let's look at the last one. We have the hypothesis, but we don't have the conclusion, because C is always false. So this is false. But that's the same truth table as P implies, this is the same column as P implies Q. So these two things are logically equivalent. Now, what is the purpose of this strange thing? This thing is called reductio ad absurdum, which is Latin, and it means to reduce to something absurd. This is saying reduces to a contradiction. How is this a useful thing? Well, in logical arguments or mathematical proof, if you can assume some premise and then, working logically from that premise, come at a statement that is absurd or always false, then you know your premise is false. Okay, so we can show that P implies Q by showing that if you were to have P and not have Q, then something would be wrong with the universe. Okay, that would be one way to show an implication. If P happens, then Q always happens. So if you happen to have P and not Q at the same time, then all hell breaks loose and we have some sort of contradiction somewhere. So we'll take a look at that more later. For right now, we'll just leave this one at that. Okay. So we've already talked about this. The contrapositive is not Q implies not P, and it's equivalent to the implication. And so here's a logical implication. If J does not play lotto, then J will not win the jackpot. So that is a logical statement. It is an implication statement involving two simple statements. J does not play lotto, and J will not win the jackpot. Let's write the contrapositive of this statement. The contrapositive is also an implication, but we switch things around. Now the conclusion becomes the hypothesis, but we have to negate it. We say, if J wins the jackpot, then J does play lotto. These two statements are exactly the same. They're logically the same. One is the implication, the other is the contrapositive of that implication. And they are logically equivalent. And so we could use either of these two statements interchangeably. Perhaps we might have reason to favor one or the other based on previous sentences in our argument. Okay. Negation is giving the opposite of a statement. So let's do an example with negation. Negate the following. The Earth's orbit is elliptical, and a year has 365 days. So the Earth's orbit is elliptical. We'll call that P. and a year has 365 days. We'll call that Q. This statement is P and Q. That's what this statement is. Now, we are supposed to negate P and Q. How do we do that? Let's scroll back up for a moment. The negation of P and Q is that statement right there. Not P and Q is logically equivalent to not P or not Q. That's one of De Morgan's laws. This is logically equivalent to not P or not Q. So now we're going to translate this back into English. And the statement is now the Earth's orbit is not elliptical, or a year does not have 365 days. All right, we're going to do one more example. This is probably the most complicated example for today, and then we'll get to the homework assignment. We're going to show the following logical equivalence. P and not R implies Q implies R is logically equivalent to not P and not R, or Q implies R. Okay, this is the statement we want to show logical equivalence with. And let's look at this for a moment before we go into detail. We see P and not R in both sides here. And we see Q implies R, both sides there. So that's going to be some of our building blocks when we weight the truth table. We're going to look at P and not R, and Q implies R as well as we build this truth table. So we need P, Q, and R. True, 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 false, 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 true, true, false, false, true, true, false, false, true, false, true, false, true, false, true, false. Now let's look at P and not R. We're looking at the first column and the third column now for this and statement. We get false, true, false, true, false, 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 false. Now we look at Q implies R. Whenever Q is false, this is automatically true, because when the hypothesis fails, the implication is automatically true. And now we fill in the rest of them. Q and R being true, this is true. Q being true and R being false, this is false. Both true, true. There we go. Okay. So now we're ready to take a look at this first combined statement. P and not R implies Q and R. Implies Q implies R. Now, this is an implication again, and the hypothesis of this implication is P and not R. So, whenever this column is false, this whole implication is automatically true, because when the hypothesis fails, the implication is true. So I can automatically throw in a lot of trues here without even thinking. Every time there's a false in the column that I've underlined over there, I put a true here. Okay, now I have to actually think for the remaining two spots. I have P and not R, but I do not have Q implies R. So this would be a bad situation. This is false, and this is true. So that is the left-hand side of what we're trying to show the logical equivalence of. And now we got to look at the right-hand side. Not P and not R, or Q implies R. So this is an OR statement with the opposite of this column and this column. As long as the opposite of the first column is true or the second column underlined is true, this is fine because it's an OR statement. So this is fine. This is not good because the opposite of the opposite column is false and the second column is false, so neither of them are true. Now we're good. We're good. We're good. Fine. Yes, if the opposite of the second column is true, we're fine. So the rest of these are all fine. Okay. And now we see that those last two columns are identical. And once you have those last two columns being identical, you have shown logical equivalence. That's all it takes. Okay, the homework for this section is going to be 6, 8, 10, 14, 18, 24, 26, and 28. So please take some time to get started, and you can clear up any questions you might have or challenges with me now.